Good afternoon, everyone. My name is Raymond and I'm going to discuss thermometers. For those who don't know what a thermometer is, it is basically a device used to measure temperatures. And here is an example of it. Thermometers can be classified as an actuator. Why is it so? Because it accepts energy in the form of thermal or heat and produces movement. The one that I am going to discuss is the liquid in glass thermometer, which is an old type. And we know that there are new types, but the principle behind is basically the same. The principle that is used for this is thermal expansion. So obviously, if the temperature is warm, the molecules in the liquid tends to move fast, making the liquid rise. But when the temperature is cold, the molecules in the liquid tends to move slow, making the liquid go down. Liquid in glass thermometer is around 100 years. The liquid that they are using is typically mercury and alcohol. But since mercury is very dangerous, nowadays they are now just using alcohol. Another example of a thermometer is a thermistor or electrical resistance, which is discussed further by our group mates, but I will just explain it a little just for an example. So, if we have a piece of metal conducting electricity, the ability to produce electricity depends on the temperature. So the hotter it gets, the greater or lesser the resistance depending on the metal that is used. So it can be used to measure, to act as a thermometer. Another example of a thermometer is a temperature-sensitive strips. Another example is a temperature-sensitive strip. It is very common nowadays. This can be buy to the shop and you can put it on your forehead and will tell you your temperature. This is generally used for a very inaccurate things, but it is basically a chemical strip and the chemical reacts according to the temperature. The color of the chemical depends on the actual temperature of the surrounding. Remember that a thermometer is not something like this. A thermometer is simply a device which measures a change in size, color, or whatever depending on the temperature. It is a physical change that gives you a measure of a temperature.
And I'm going to discuss bimetallic strip. The bimetallic strip is a device used to convert temperature change to mechanical displacement. For example, this is a bimetallic strip. It is consists of two different metals with different thermal expansion coefficient. If this is the metal with greater thermal coefficient, and this is the lower thermal coefficient. When we apply it here, due to thermal expansion, the bimetallic strip will expand like this. The difference in expansion will force the bimetallic strip to bend. Some applications of this bimetallic strip are thermometer, thermostat, and in fire alarms. We're going to proceed to the applications of the bimetallic strip. For example, this is the thermometer. This is the stem of the thermometer. This is the bimetallic strip or coiled bimetallic strip, and this is the gauge. For simplification of discussion, we will use this representation for the bimetallic strip and the gauge. This bimetallic strip is coiled, and a coiled bimetallic strip is more sensitive on temperature. So, due to small change in temperature, it will expand. For example, the initial temperature of the object is 20 degrees Celsius. Here is the bimetallic strip. When it is heated and the temperature rises to 50 degrees Celsius, the bimetallic strip will expand and force the pointer to move this direction. And when it is heated, it is cold, the temperature will go down to its initial temperature. Then the bimetallic strip will also go to its initial length. Second application is for the fire alarm. Using this simple circuit diagram, I am going to discuss the application of bimetallic strip in fire alarm. When there is a fire, the temperature will rise, and because of the rise in temperature, the bimetallic strip will expand. We see here that when there is no applied increase in temperature, the bimetallic in this point is not connected. But when there is a fire, this bimetallic strip will expand and bend going here. Because of the expansion, the circuit will be triggered or short-circuited, and this fire alarm will alarm. This simple circuit work, I saw a video in YouTube, and this is the video.
This wonderful kit has been designed by LG of Korea. It's essentially a fire alarm, the heart of which is a bimetallic strip, and everything is mounted in this plastic box. Here is the circuit with the bimetallic strip, alarm, or LED, and a battery. Once the circuit is completed, the alarm rings and the LED lights up. Now you mount this on the lid. You can see the bimetallic strip, the battery, the LED, and the alarm is on the lid. When the circuit is completed, the LED lights up and the alarm rings, a warning sign. Now, you put the battery inside this plastic box, and the LED actually goes in a hole in the box, which is the top of a fire tender. Now, close the box. On top is the alarm and the bimetallic strip. Then place a lighted candle below the bimetallic strip. When it is going to bend, complete the circuit, the alarm will ring and the LED will glow. This is the heart is a bimetallic strip, which when heated, bends, completes the circuit, lights the LED, and sounds the alarm. This is the heart of this fire alarm.
Thermostat regulates the temperature of the room. Here, one end of the bimetallic strip, which is coiled, is at the fixed point. Another end of the coiled bimetallic strip is connected to the mercury switch. When the room reaches the desirable temperature or the set temperature, the bimetallic strip will also reach its desired length where it can be switched on or off the mercury switch.
Hi guys! Another example of a thermal transducer is a thermostat, and later it will be discussed further. What is a thermostat? It is a device that automatically controls heating or cooling equipment in such a way as to maintain a temperature at a constant level or within a specified range. The thermostat generates signals, usually electrical, to activate relays, valves, and switches when the temperature rises above or falls below the desired value. The sensing element measures changes in the temperature and produces desired effect on the transducer. The transducer converts the effect produced by the sensing element into a suitable control on the device, which affects the temperature. When the strip is cold, the contacts are closed and current passes through the thermostat. When it gets hot, one metal expands more than the other, and the banded bimetallic strip bends up or down, opening the contacts and preventing the currents from flowing. Thermostats most probably uses a bimetallic strip to sense temperature. As we can see, the electrical contacts are closed. When the temperature goes above a set point, the contact is closed. The closed contact turns on the compressor, which starts cooling the refrigerator. In the figure below, we can observe that the electrical contacts are now open, and the movement of the strips is this way. After a bit, the temperature goes low enough and the contact opens, turning off the compressor. This cycle continues. A refrigerator thermostat is the controlling component of the refrigerator cooling system. Once a user sets the desired temperature, the thermostat maintains that temperature by sensing internal fluctuations and prompting the compressor to turn on or off in response to those changes. When the refrigerator is appropriately adjusted to the designated temperature, the thermostat stops the flow of electricity to the compressor, stopping it from cooling the appliance. When the refrigerator thermostat detects too much heat, the compressor turns on. To understand further, here is an animation on how a thermostat works on a refrigerator.
To cool both the refrigerator and freezer, the control allows voltage to travel to the start relay and compressor, as well as to the condenser fan motor and evaporator fan motor. Once the proper temperatures are reached, the control shuts off the voltage to the cooling system. Keep in mind that it's normal for the temperatures to vary throughout this cycle.
Hi guys, I'm Mark Zadi, Sir Don. Hi sir. Now that we've learned the other kinds of thermal transducers, I will now present to you heat flux sensors. Heat flux sensors is a transducer that generates an electrical signal proportional to the total heat rate applied to the surface of the sensor. Wait, let's pause here. What is heat flux, by the way? Let's check our friendly Google search engine about that. Okay, so heat flux. So let's click on Wikipedia. Let's wait for a while to load. Okay, so heat flux or thermal flux is the rate of energy transfer through a given surface. The SI derived unit of heat rate is joule per second or watt. Heat flux is the heat rate per unit area. The heat flux can have different origins in principle, convective, radiative, as well as conductive. Heat flux sensors are known under different names, such as heat flux transducer, heat flux gauges, and heat flux plates. Some instruments that actually are single-purpose heat flux sensors like pyrometers for solar radiation measurement. Other heat flux sensors include Gardon gauges and Schmidt-Bolter gauges. These are the applications of heat flux sensors. Determining thermal properties of materials, monitoring structural heat transfer, process control and heat treating rolling mills and glass productions, effective for convection, conduction, and radiation heat transfers, determining heat loss and insulation efficiency in housing, and analyzing aerodynamic wind tunnels. The total heat flux is composed of a conductive, convective, and radiative part. Depending on the application, one might want to measure all three of these quantities or single out. Again, wait. For the better of this discussion, let's define the parts of total heat flux first. Conductive is the transfer of heat energy by microscopic diffusion and collisions of particles or quasi-particles within a body due to a temperature gradient. The microscopically diffusing and colliding objects include molecules, electrons, atoms, and phonons. They transfer microscopically disorganized kinetic and potential energy, which are jointly known as internal energy. Conduction can only take place within an object or material, or between two objects that are in direct or indirect contact with each other. Convective heat transfer, often referred to simply as convection, is the transfer of heat from one place to another by movement of fluids. Convection is usually the dominant form of heat transfer in liquids and gases. Although often discussed as distinct method of heat transfer, convective heat transfer involves the combined process of conduction and advection. Radiative transfer is the physical phenomenon of energy transfer in the form of electromagnetic radiation. The propagation of radiation through a medium is affected by absorption, emission, and scattering processes. So, we will only discuss three large fields of application due to time constraints. So, let's start with application in meteorology and agriculture. Soil heat flux is the most important parameter in agrometeorological studies, since it allows one to study the amount of energy stored in the soil as a function of time. Typically, 2 or 3 sensors are buried in the ground around a meteorological station at a depth of around 4 centimeters below the surface. The problems that are encountered in soil are threefold. First is the fact that thermal properties of the solid are constantly changing by absorption and subsequent evaporation of water. Second, the flow of water through the soil also represents a flow of energy. The third aspect of solid is that by the constant process of wetting and drying, and by the animals living on the soil, the quality of the contact between sensor and soil is not known. The second large application is in building physics. In a world ever more concerned with saving energy, studying the thermal properties of buildings has become a growing field of interest. One of the starting points in these studies is the mounting of heat flux sensors on walls in existing buildings or structures built especially for this type of research. The measurement of heat flux in walls is comparable to that in soil in many respects. Two major differences, however, are the fact that the thermal properties of a wall generally do not change, and that it is not always possible to insert the heat flux sensors in the wall, so that it has to be mounted on its inner or outer surface. The last part of large applications is that in medical studies, the measurement of the heat exchange of human beings is of importance for medical studies and when designing clothing, immersion suits, and sleeping bags. A difficulty during this measurement is that the human skin is not particularly suitable for the mounting of heat flux sensors. Also, the sensor has to be thin. The skin essentially is a constant temperature heat sink, so added thermal resistance has to be avoided. Another problem is that the test persons might be moving. The contact between the test person and the sensor can be lost. For this reason, whenever a high level of quality assurance of measurement is required, it can be recommended to use a self-calibrating sensor. Other parameters that are determining sensor properties are the electrical characteristics of the thermocouple. The temperature dependence of the thermocouple causes the temperature dependence and the nonlinearity of the heat flux sensor. The nonlinearity at a certain temperature is in fact the derivative of the temperature dependence at that temperature. However, a well-designed sensor may have a lower temperature dependence and better linearity than expected. There are two ways of achieving this. First is that the thermal dependence of conductivity of the filling material and of the thermocouple material can be used to counterbalance the temperature dependence of the voltage that is generated by the thermophile. Another possibility to minimize the temperature dependence of a heat flux sensor is to use a resistance network with an incorporated thermistor. The temperature dependence of the thermistor will balance the temperature dependence of the thermophile. Now that we have a little background about its uses, let's now check its properties. As shown in the figure, heat flux sensors generally have the shape of a flat tape, a sensitivity in the direction perpendicular to the sensor surface. Usually, a number of thermocouples connected in series called thermophiles are used. Generally, advantages of thermophiles are their stability, low ohmic value, good signal-to-noise ratio, and the fact that zero input gives zero output. Disadvantageous is the low sensitivity. To promote uniformity of sensitivity, a so-called sandwich construction, as shown, can be used. The purpose of the plates, which have high conductivity, is to promote the transport of heat across the whole sensitive surface. The intrinsic specifications that can be attributed to heat flux sensors are thermal conductivity, total thermal resistance, heat capacity, response time, nonlinearity stability, temperature dependence of sensitivity, uniformity of sensitivity, and sensitivity to lateral fluxes. I think that's it for us. I hope you learned something, and let me leave you with these videos from YouTube showing actual experiments using heat flux sensors.
Again for Gregorio, and I will talk about bolometers. A bolometer is a device that has the ability to measure radiation. It has been invented by Samuel Langley on 1878. He invented this device in order to study the sun and its effect on the Earth's weather. NASA has been using this device numerous times, and one of it is the Earth Budget experiment. But how is it a transducer? The bolometer is a transducer because it can convert radiation into electrical signal, and this is how it works.
This is a badly made bolometer example. The black metal plate is the photon absorber. The white box is the thermometer. These are the connecting leads, and this is the heatsink. As you can see, there is an electrical isolation between the heatsink and the thermometer. The two of them should only be thermally connected. For example, this flashlight is a star in the universe. Its radiation will affect the resistance of the black metal plate. It has been colored black so that it can absorb more photons. The change in resistance will be measured through the connecting leads.
This is the typical bolometer circuit. The bias voltage connected to a load resistance, then the bolometer. The load resistance should be greater than the bolometer resistance so that any change on the bolometer resistance will not greatly affect the current. If we focus on this part of the circuit, it looks like this. The absorber, the thermal link, and the heatsink. And this is the radiation from what is being measured. The formula for the resistance RO and B are constants. That is the end of my discussion, and thank you for listening.